Hello everyone, my name is Aaron Black on behalf of Jacel Consulting, and I'm here alongside my colleagues Loretta, Catherine, Jade, and Elvin, and today we'll be discussing the disposal of cannabis biomass waste on behalf of our client, the British Columbia Ministry of Agriculture. Today's presentation has been split up into three different sections. In the first section, we'll cover the introduction, problem definition and scope, and the constraints and criteria. Next, we'll move on to the design alternatives and our final design for the problem. Moving forward, we'll touch on the social, economic, and environmental impacts of our final design, and we'll wrap it all up from there. On October 17, 2018, the Cannabis Act of Canada came into effect, introducing new regulations around the industry. In 2015, the domestic market production of cannabis was $50 million, whereas in 2018, the market production spiked at $1.6 billion. The number of Canadians using cannabis of any frequency increased by 15% from 2014 to 2018. Of the three largest provinces by population, being Ontario, Quebec, and British Columbia, it was found that 20% of British Columbians consumed cannabis in the past 3 months. It was found that some British Columbian cultivating facilities use incineration to dispose of cannabis biomass waste. This disposal method generates large volumes of greenhouse gases which can contribute to climate change, the effects of which are well documented. In addition to the environmental risk these pollutants pose, they pose an additional risk to human health. Incineration process also produces unpleasant odors to those living in the vicinity. Economically, incineration is a costly process due to operation and maintenance, large capital costs, and high energy demands. The scope of this problem has been based around the average British Columbian cultivating facility by summing the production, size, and waste generation of all facilities and dividing by the total number of facilities in the province.
The constraints are very similar to the scope as we are constrained by the average British Columbian cannabis cultivation facility. Constraints of the design must be capable of disposing of the 51,000 kilograms of biomass waste a year. It must stay within the available space of the facility, and the design must also comply with the regulations set by the Canadian government and the British Columbian government, such as the composition of the biomass waste when it is disposed. In this case, we must follow Schedule 2 of the Cannabis Act by the Canadian government, which states that the biomass or the non-viable seeds, mature stalks, fiber derived from the stalks, and the roots of the plant. The criteria of the design were separated into four categories that we decided were the most important to the British Columbia Ministry of Agriculture. The first one is environmental. Minimizing emissions such as greenhouse gases are very important, as well as the energy consumption of the design. The next one is health. Minimizing the greenhouse gases such as CO2 and methane emissions to reduce harmful health effects to the public. Note that in the environmental impact criterion, the CO2 and methane are separated since they have different impacts on the environment. However, for health impact, CO2 and methane have similar health effects such that it was feasible to combine the two into one criteria. Thirdly, we wanted to create a feasible design that was economically efficient. And lastly, the social impact of the design is important as well since the government likely cares about the public opinion and their impact of the design on their constituents.
The three design options that were considered as alternatives to incineration were compost, landfill, and anaerobic digestion. Compost is a mixture of organic matter that is set to biodegrade under specific conditions dependent on microbiological activity, with the ideal end product being plant fertilizer. Landfills involve burying the waste and covering it with soil. And anaerobic digestion is a biological process in which microorganisms break down biodegradable material in the absence of oxygen to produce biogas, which can be used as fuel.
Ranking system of the criterion in determining the best possible design from the proposed solutions. The final design is determined by first ranking the criterion against each other from the perspective of the ministry. This ranking system for the criteria is used as a point system in the decision matrix. The criterion listed in the second column and in the first row are the same. Each criteria is then compared against each other, getting 1 point if it is deemed more important.
This is the decision matrix for comparing our design alternatives for disposing the cannabis waste. These rankings are determined by using models such as WARM and literature review for each design alternative. It can be seen that composting is the best design solution for this project because it gained the most points.
In terms of the actual batch characteristics, the following parameters must be carefully controlled to ensure optimal productivity of the pile: the carbon to nitrogen ratio, the moisture, and the temperature. The reason that the carbon to nitrogen ratio is so crucial is due to the fact that these elements contribute to the microbial health of the organisms that will be decomposing the organic matter. Specifically, they need 25 parts of carbon for every 1 part of nitrogen. These organisms use carbon as a source of energy and nitrogen for building new cell structure. In the process, much more carbon is burned, so they need much more carbon than they need nitrogen. Literature research reveals the carbon and nitrogen content of each component of the pile. As listed in the leftmost table, the cannabis waste has the highest nitrogen mass fraction value at 2.78%. Since the percent carbon is only 44.5, a quick division reveals that on its own, the cannabis waste only has a carbon to nitrogen ratio of 16:1. This low carbon content is a common obstacle for compost projects, and thus additional ingredients such as cardboard and sawdust must be added as an additional streams to the pile. For the given 980 kilograms of cannabis waste that is produced on a weekly basis, 500 kilograms of cardboard and 500 kilograms of sawdust will be required to produce a carbon-nitrogen ratio of 25:1. Moisture is the second parameter that must be considered in the compost pile. Again, it is a requirement to keep the organisms healthy and crucial for promoting their optimal microbial activity levels. Too little moisture will impede activity from initiating because the organisms will go dormant or potentially die, whereas too much will block the airflow and oxygen is unable to reach all parts of the pile, leading to anaerobic activity and will bring about foul odor. Soil moisture probes are an inexpensive mechanism of monitoring the status of the pile. The ideal moisture level is 50 to 60%. The moisture content for each component is listed in the table displayed. The moisture of the cannabis biomass waste was estimated using an average of similar plants from literature, and the value can be as high as 35%. Sawdust often contains over 50% of moisture as a byproduct of wood biomass. Finally, cardboard has the lowest moisture content with only 12%. Again, when using the 980 kilograms of cannabis waste, 500 kilograms of cardboard, and 500 kilograms of sawdust, the batch just reaches 50% moisture levels. It is good to keep the levels on the lower end of the range because it is easier to manually add water to the pile rather than if the moisture level was too high, and then the ratios of the ingredients would have to be adjusted. For example, adding more cardboard or other dry materials with low moisture content, while still maintaining the crucial carbon to nitrogen ratio.
The temperature of the compost pile must be maintained at the optimal level for the microbiological activity. This range is between 40 and 60 degrees Celsius. Temperatures above 65 degrees Celsius will cause the microorganisms to die and the compost process will not be carried out. The microbiological activity also causes the temperature to increase, so to mitigate this, the compost pile should be turned when the peak temperature is reached. This allows for an even distribution of the temperature so there's no hot spots throughout the compost pile. This should be monitored with a temperature probe.
Now that we know the design considerations required to optimize and maintain the pile, we can now discuss the process of composting. There are 3 main stages of composting, the first of which is the active composting stage. The whole process is driven by living creatures called microbes, and just like other living creatures, they need to be in the right environment to develop. This is where moisture, temperature, carbon-nitrogen ratios, and active aeration combine to drive the process. The second stage is curing. During this stage, temperature and active oxygen supply will be reduced, but the organic material will still continue to decompose at a slower rate. The stabilization of pH, temperature, and humidity begin during this curing stage. The third and final main stage of composting is storage. This stage ensures that the compost is fully matured after the curing stage before it is ready to be used. Immature compost can stop seeds from germinating and thereby preventing the survival of plants. A single active composting pile is required to manage a volume of 58.6 meters cubed per week that is comprised of a mixture of cannabis waste, cardboard, and sawdust. The dimensions of this active compost pile will be 2 meters in height, 1.5 meters at the base, and 19.53 meters in length. It is suggested to actively aerate the compost for at least 4 weeks. Therefore, the facility will actively aerate 4 piles at a time. The curing pile size will be a summation of the 4 weeks of active composting, where the duration will also be 4 weeks. However, During the curing stage, the compost pile will reduce to 50% of its initial volume. Thus, the total curing pile volume for the 4-week period will be 116 meters cubed. The dimensions are 1.8 meters in height, 3.75 meters at the base, and 17.19 meters in length. The storage phase will be a accumulation of compost after the curing stage is finished. Here, the compost will sit for an additional 9 weeks to ensure the compost is fully mature. The total volume for the 9-week period of compost will be 261 meters cubed, where the dimensions of the storage pile are 2.4 meters in height, 8 meters at the base, and 13.6 meters in length. The introduction of oxygen will be supplied through a single blower, pumping air attached to a perforated pipe under each pile, as shown. Each pile must be placed 6 meters apart in order to provide enough space to load and remove each pile from the active composting stage. Next, we will discuss the equipment sizing and energy requirements. A blower with the capacity to supply 277 cubic feet per minute to 4 piles with a combined mass of 7,920 kilograms in parallel configuration for the active composting is required. For 277 CFM, a blower was selected and the energy input was determined to be 480 watts. While running continuously, the annual energy consumption will be 15.1 gigajoules. On the other hand, the perforated pipe that is connected to the blower will have a nominal size of 6 inches, and just enough length to be inserted over the entire length of each pile. Furthermore, the piping material was decided to be PVC due to the low cost and resistance to chemical rotting, corrosion, and abrasion.
Finally, using the criterion first described in its presentation, we will go through each one, starting with the environmental impact. The waste reduction model is created by the U.S. Environmental Protection Agency to help predict greenhouse gas emissions of carbon dioxide from waste management practices. In the case of our design for composting, 330 kilograms of carbon dioxide is emitted per week. The model uses emission factors. This tool is used in air quality management and is a method to relate the quantity of pollutants released in the atmosphere from specific activities, in this case, windrow composting. An emission factor is a representative value expressed as the weight of the pollutant divided by the unit weight volume of the pollutant causing activity. These factors are averages from various sources of air pollution from composting. The equation to determine the emission is the amount going through the composter, the throughput, multiplied by the emission factor. The table seen on the slide is indicative of the different emissions emitted from the composting system a week in kilograms.
The health impacts are minimized as the final design chosen emitted the least amount of methane and CO2 out of all the design alternatives.
The economic success of this design is measured as the minimization of the capital and annual costs. The capital costs of this design include a blower fan, PVC piping, an extension cord, and a recommended cardboard shredder, which can use cardboard from within the facility for the composition of the compost. The operation includes energy to run the fan, as well as the cost to purchase sawdust and cardboard.
Lastly, the social impact is minimized as composting does not generate large amounts of noise as a disposal method. As for odor, the smell is minimized via the frequent turning and the large addition of dry brown materials such as sawdust and cardboard that make a huge impact in reducing odor. And finally, aerobic composting is much less odorous than anaerobic composting.
To conclude, the static aerated windrow composting system has been presented as the best design for the British Columbia Ministry of Agriculture. We would love to hear your feedback and answer any questions at this point. Thank you for viewing our presentation.